Let's find the electric field for a ring with a uniformly distributed charge along the axis of the charge which comes out of the screen. And we'll label this Z. So we'll denote the radius of the ring as capital R and the radial distance from an element of charge along the ring to a point on the axis of the ring as R. And the vertical distance from the center of the ring to the point on the axis will denote Z. And note that the electric field vector produced by this element of charge here is going to be acting in this direction, radially from that differential charge element. And that's our differential electric field vector. So by symmetry, an element of charge on this side is going to produce an electric field that's going in this direction. And therefore, due to symmetry, the horizontal components of these electric field vectors will cancel each other out. So therefore, the component of the electric field vector that's acting in the vertical direction is going to contribute to the net electric field in the vertical direction. And therefore, if we look at an element of the electric field in the vertical direction produced by a single differential charge, well, that's going to be equal to the magnitude of the electric field vector cosine theta, where theta is going to be the angle between the vertical axes and the electric field vector. And using our integral for the differential electric field produced by a single infinitesimal element of charge, well, what we have is 1 over 4 pi epsilon naught by the differential charge over r squared. And cosine theta is going to be equal to the adjacent on the hypotenuse. So that will be z on r. And now if we integrate both sides of this equation and make our substitution for r using Pythagoras, well, we get our net electric field in the vertical direction is equal to 1 over 4 pi epsilon naught by the integral over the charge over r squared, which by Pythagoras is z squared plus r squared, and that's multiplied by z over r, which is the square root of z squared plus r squared. And we can take z outside the integral because the element of charge does not depend on the z direction. So you can imagine that dq is equal to the linear charge density multiplied by the differential element of charge along that circle. So that would be ds, or the arc length of that differential element, which you can rewrite as lambda by r d theta. Okay, so you can compute this arc length using d theta by the constant radial distance from the center of that ring. So we get z over 4 pi epsilon naught by the integral of lambda r, which is constant, and we have d theta in the numerator, z squared plus r squared to the 3 on 2. And therefore, given we're integrating over theta, we can see that z and r are both constant. So we can take all the z and r terms outside the integral. So what we have is the following result. And we integrate over theta, and our limits of integration are from 0 to 2 pi. So therefore, we get lambda by 2 pi r when we evaluate that integral, and that's multiplied by z over 4 pi epsilon naught by z squared plus r squared to the 3 on 2. And that's our final electric field. Now one observation we can make is that lambda by 2 pi r gives us a total charge around that ring, which I'm going to call Q. So we can write this as Q by Z on 4 pi epsilon naught by Z squared plus R squared to the 3 on 2. And if we take the limit as R goes to 0, so this ring collapses into a point charge, well, what we get is E approaching QZ over 4 pi epsilon naught. And when R approaches 0, this term drops off, and what we get is Z cubed in the denominator. So in other words, the electric field approaches Q on 4 pi epsilon naught Z squared, or that of a point charge. So this result makes sense, and I'll see you in the next video.